Okay, today we're going to go through the October 23 paper for Unit 2 Physics International Edexcel for the Year 12 students. So the Unit 2 exam is normally done in May, so they'll be coming up next week, I think. So the Unit 1 is this week, Unit 2 is next week, and Unit 3 is the following week. So I just use this as a mock with my students, so I'm going to go through the answers. Okay, first question is the formula for a diffraction grating is given here. So which of the following quantities has no units? Well, the answer is A. N has no units, it's just an integer, and the other ones all have units. So lambda is meters. D, obviously, in the equation is also a distance, however small, and theta is in degrees. Okay. So question 2 is a current potential difference for a diode shown. See, on the negative bias there's a very slight current in the negative direction, and then the typical shape of the graph is that it starts increasing at around 0.6, 0.7 volts in this case. Okay, so they want you to know which of the following statements is correct for this diode. The diode does not conduct in the reverse direction. Well, you can see from here that there is a very slight conduction, very small current, and it depends on, obviously, if you're just using a normal ammeter, you won't be able to read it. And the second one, the resistance of this diode in the reverse direction is infinite. Well, that can't be true if there's a very small current shown in the graph. And C is the correct answer. The resistance of the diode decreases above 0.7 volts. So above 0.7 volts, the current shoots up. If the current shoots up suddenly, it means the resistance is decreasing. Okay, and D, just to complete the 4 options, this diode does not conduct when the PD is below 0.7. Well, it's not true, because you can see it starts going up very slowly before it gets to 0.7 volts. Okay. Again, it depends on your sensitivity of your meters, whether you can detect it or not. That's question 1. 2. Question 3 says which of the following would increase the detail in an ultrasound scan. So this is an area which may not be taught very clearly during the course, but when you do the exam you'll notice the questions that come up in it. So increasing the duration of the pulse, well, this will reduce detail, because the pulses will be, if they're increase in duration, will be less sharp pulses. So it's kind of like a fuzzy image. You want it to be sharp. Okay? Increasing the frequency of the ultrasound. So if you increase the frequency of the ultrasound, you're going to have shorter pulses, and that will increase as does the opposite of this. This is what you want, shorter pulses of sound, so you can get a sharper pulse, and therefore you can get more detail with it. Increase the intensity doesn't affect the detail. It will affect, for example, the brightness of the image, but not the detail. Increasing the wavelength, well, if the wavelength goes up, the frequency goes down. Again, this will reduce the detail, like in A. Okay? So once you know that frequency is linked to period, so duration of the pulses, we're talking about the period. Okay? And from knowing that we want it to be low period, high frequency, yeah, that's what will increase it. And obviously, high wavelength is a low frequency, so it's the wrong way around. Hope it makes sense to you. If not, you just need to think about it. In a current carrying wire, copper wire, the drift velocity of the electrons is very small. Which of the following best explains this? Okay, so we really are focusing on this equation, which is on the formula sheet. The answer you can see is D. The charge on an electron is very small. Well, if Q is very small, then V should be very large if the other two don't change. So that's not going to be correct. The cross-sectional area of the wire is very small. Well, if the cross-sectional area of the wire is very small, yeah, if the cross-sectional area of the wire, velocity, if the cross-sectional area is very small, so I've done this, the arrows the wrong way. If the cross-sectional area of the wire, that's what's confusing me. If the cross-sectional area is very small, going down, then the velocity must go up to compensate for it, to keep the current. So it's not correct. And the current in the wire is very large. If I is very high and those are the only things changing, then V would also be high. Okay? Now, the reason the drift velocity is very small is because you have so many electrons per unit volume, free charge carriers, yeah, is very large. So if n is very, very large, then V doesn't need to be large to maintain that current. Okay, it's just a large number of electrons which drift slowly, and you multiply them together, you get a measurable current. Okay, question 5. The graph shows displacement varying with time, yeah, for a particular point as a wave passes. So basically the point goes up and down, just like if you put a duck on water, a rubber duck will go up and down as the waves pass by. Okay, so which of the following statements is not correct? The time period can be determined from the graph. That is correct. Yeah, because obviously time period would be the distance between peak, and you can measure it off the scale. The wavelength can be determined from this graph. No, it can't, because you don't have the wavelength as the distance between peaks, where that would have to be a distance scale. Yeah, so we automatically know it's B, and the fact that they're longitudinal or transverse, it either can be plotted longitudinal or transverse as a displacement time graph. Okay, because remember they're talking about displacement at a point, yeah, as it changes as the oscillations go through that point. Okay, so it can happen with transverse and longitudinal waves. So here you've got a standing wave pattern, yeah, 6 and 7, yeah. So the length of the wire V from Y, V to Y is 0.6 meters, which you can see from V to Y you've actually got 1.5 waves. So that's 1.5 wavelengths, because this is a complete wavelength, is a peak and a trough, yeah. So this is one complete wavelength from V to X, and then another half wavelength again. So we know 1.5 lambda is 0.6 meters. They want you to work out the wavelength of the standing wave, so you just change the subject of the equation, and you'll see it's 0.6 divided by 1.5, which is 0.4, which is B. Question 7, which of the following sections of the string would be in phase with each other? So with standing waves, basically when this bit goes up, this bit goes down, and this bit goes up, yeah? When this bit goes down, this bit goes up, and therefore this bit will be the opposite. So each half wavelength is oscillating in phase with itself, and with out of phase with the next section of the wave. Okay, so we're talking about sections. So VW is a section, WX is a section, and XY is a section. So when VW and X and WX, so VW going up, WX going down, so that's not true. WX here, if that's going up, XY here, this will be going down, so they're opposite phases. Okay, so they'll be out of phase. VW here, and then XY right at the end, then this is going up, this is going down, this is going up. So this, in this case, when this goes up, this will be coming down, and this will be going up. So C, at the same time, VW and XY would both be going up, and then alternately, when they're going down, they will both be going down at the same time. And no sections are in phase, but obviously that's not true because C is in phase. Okay, so question 7 done. Question 8, a string is placed under tension, a wave travels along the string. So a second string has the same mass but twice the length. So here we're talking about mass per unit length, mu. A wave travels along the string with the same velocity as the second string, same velocity as the first one. So V2, they're telling us the two velocities are equal. Now the equation that links tension and the velocity is this one. V equals T tension over mu all over a square root sign, or all under a square root sign. Okay, so which of the following is the tension in the second string? So I'm going to get rid of the square root sign, change the subject to tension because that's what we're looking at. So we know that tension will always be equal to mu times V squared. Now we know that the second string has the same mass but twice the length, that means this mass per unit length of the second string will be half of the first string, same mass. So once you do that, you can say tension 1 is going to be mu1 V1, tension 2 would be mu1 over 2, yeah, times V1. You can then divide tension 1 by tension 2, and you'll see that it will be half because they're the same equation, except the second one is divided by 2. So if you divide this by this, you will get a ratio of 2. So the answer is C. Question 9, energy levels in a hydrogen atom. So you got from 0 to minus 1.36 and so on. They've shown you 4 different energy levels. And they want to know which of the following expressions is equal to the lowest frequency of light possible. The lowest frequency of light possible is the smallest transition possible, which if you work it out the way I have, the smallest transition possible is from this level to this level. Okay, so when an electron jumps down that level, it will give a frequency corresponding to that energy, which is equal to hf, where h is Planck's constant, and then f will be equal to the delta E over h. Okay, so delta E is the difference between those two levels, and don't forget that the energy is in 10 to the minus 19 joules. I was just doing it quickly, so you've got to make sure you've put the numbers and 10 to the minus 19 in there for each one, and then you divide it by h, so it gives you the answer D. Okay, and finally question 10. 2 photographs X and Y were taken of the same car windscreen. Photograph Y was taken through a polarizing filter. So this one's not taken through a polarizing filter. Now, so they want to see if you understand what a polarizing filter does. Which row of the table is correct? Okay, light is transmitted through the windscreen. Yes, but we know light is transmitted through the windscreen. So in terms of rows, when it's transmitted through, it's unpolarized, okay? But when it's reflected off the windscreen, it will normally, just the same as water, so light off a pond, for example, at an angle, will come off as being polarized when it reflects off it. So the line that has both ticks is line C, okay? So that's the end of the multiple choice section, yeah? And I'm going to do a few more of the short questions and stop the video at an appropriate point to see. I'm just seeing how many questions there are. So there's 18 questions in this paper. Okay, so we're going to go to the next one. So that's 10 multiple choice questions done. And section B starts with question 11. And it says some animals use pulse echo techniques to collect information about their surroundings. Okay, describe how this technique provides information about the surroundings. Well, sound waves, obviously. Presumably they're talking about sound waves, aren't they? Like bats use sound to detect where the walls of the cave are, for example, and also their prey. Sound waves reflect off surrounding surfaces or solid objects. Okay, so that's the first point that you need to make, that this is reflection that occurs. Time for the waves to return is detected by the animal. So it's like the animal can actually work out distance over time, or speed, yeah, times velocity, yeah. So that's what it's using. So the time can be used to determine the distance or the position of the surface of the object that's coming off, and allows them to work out the location or the distance to that object. That's how you get 3 marks. So question 12, 2 resistors are connected in a circuit as shown. So the current is going round here, splits at this junction, goes through some current will go to R1, some current will go to R2, and then over here they'll join up again and the total current will be there. So we know the total current will be equal to the 2 split currents. Each path is at voltage V, so each of these paths, resistors, are at the same voltage as the battery. So we know V1 over R1, which is I1. So remember that knowing I is V over R, we can just say this one is V1 and this one is R1, so we say V1 over R1. So if you like, there'll be a voltage across there, V1 over R1 will be I1, and you can do the same with the second one, V2 over R2. But we know that all the voltages in parallel are the same, so we can cancel out all the voltages and replace them with ones mathematically. So this is what they want us to derive. They want us to derive an expression for the combined resistances and show that it can be shown to be equal to that. Yeah, so the combined resistance, let's call it the RT. Well, we know that this is the normal equation that students in GCSE learn. Well, if you multiply it out, you'll get R2, you make the common denominator R1, R2, then this one will be R2 over R1, R2, and this one will be R1 over R1, R2, common denominator, so you can then add the tops. But remember, this is 1 over the total resistance, so you reverse the fraction and you get to that point. And how many marks is that? 3. So looking at the mark scheme, you get 1 point for realizing the current splits up, 1 point for understanding there's conservation of energy. In other words, the total voltage is the same, so that's the point that they're making there and there. And then 1 point for doing the algebra correctly. Okay? So that's question 12. Question 13, continue with electricity. Bear with me. Question 13 is using something called resistivity paper, which is paper covered with a thin layer of carbon, and you know the carbon is a conductor. Okay, so it's a non-metallic conductor. The distance between the ends of the piece of resistivity paper is 12 centimeters, so across there is 12 centimeters there. The resistivity paper is 4.2 centimeters wide, so this is the width, and then it's got a little thickness here as well, so how thick it is there. Alright, so that's what we want to look at. We're actually looking at the thickness of the layer of carbon, so that's what we're looking at. So T would be the thickness of the layer of carbon, so it may not be what I've drawn. So we got some information. The resistance between the ends of the resistivity paper, yeah, so from there to there, is 8.8 ohms. And we know from our equation sheet that R is equal to the resistivity times the length divided by the area. Okay, now if the area, by the area we mean this area at the end, because the current is going through this, so it's like your cross-sectional area here. So the area is T times W, the thickness of the layer of carbon multiplied by the width will give you the area. So I've replaced area with T times W. So this is our equation. We can then rearrange it, yeah, from there into T equals rho L over RW. So in effect, the T and the R swap places in the equation, put the numbers in, you will get to two significant figures, 1.2 times 10 to the minus 5. I should imagine you'll get one for working out the area, yeah, so one for working out the area is TW, one for putting the numbers incorrectly, and one for the answer with the units, okay? And two significant figures is what they've given, okay? And why? Because here's two significant figures, here's two significant figures, here's maybe 3, here's 2, okay? All right, so that's question 13, part 1, A. Then it continues with 13B. The student connected the ends of the resistivity paper to a cell of EMF 1.5 volts and a voltmeter is shown. So basically what's going to happen, it says the reading on the voltmeter was 1.4 volts. That's less than the EMF. So we know from the core practical that the terminal potential difference, which is what a voltmeter measures here, is 1.4 volts. That means the rest of it is lost volts. Where is it lost? Inside the internal resistance. Okay? So you have internal resistance inside your cell. Okay, so imagine you've got a tiny little resistor inside your cell, and this is your whole cell that you buy from the shop, which looks like that. Imagine it's got a tiny little resistor inside it, yeah, which you can't see. So 0.1 volts would be lost in there, okay? And here you get the rest of it outside the cell. So that's what happens to EMF. So the lost volts is 0.1 volts. So they'll probably give you a mark for knowing that. And we know that 0.1 volts, the current, is also going through the internal resistance. So lost volts will be I times little r. But to know I, we know that the external voltage here is 1.4 volts. Yeah, and we know its resistance from before is 8.8 ohms. So we can work out I here. Once you've got I, you can then put it in there to find the missing value, which is the internal resistance R inside the cell. So it gives you a value of 0.63 ohms. Two significant figures is correct because most of the values given are only given to two significant figures. Final part of this question, the connection to the right-hand terminal of the voltmeter. Yeah, the right-hand terminal of the voltmeter. So for example, this one is moved to here. So instead of it putting there, you put it somewhere over there. So it's touching the resistivity paper still, but at a length which is lower. So we know, so distance 3.0 centimeter. Well, the original length was 12, and we know the resistance is proportional to length, and we know the voltage is proportional to resistance, so we could say the voltage is proportional to length. So if you've gone down to a quarter, the voltage will, the resistance will be a quarter, 2.2 instead of 8.8. The length will be 3 centimeters and 12. So they're all in the same proportionality. So the final voltage for 3 centimeters compared to 12 will be a quarter of the value you had before, so it will go down to 0.35. So for working out, it's a quarter ratio, and one for getting the answer correct, again to two significant figures. Okay? Question 14 continues with electricity. You have a temperature sensing circuit, yeah, because it's got a thermistor in it, so the thermistor varies with temperature. Consists of a fixed resistor here and a thermistor here. As shown, the circuit supplies a PD to operate, so the circuit supplies a PD to operate a heater switch, which is in parallel to the thermistor, and the heater switch, so the heater switch is on when the PD across here, yeah, is greater than 0.7 volts. So when we got 0.7 volts, imagine you're measuring that voltage across there and there. When that voltage, so that share of the 6 volts, is 0.7 or greater, then the heater will switch on. Okay? The resistance of the thermistor varies with temperature as shown in the graph. They put it in centigrade, so this will be 0 centigrade. So you've gone from minus 20 all the way to plus 140 degrees centigrade. And the question, oh, I didn't show you the bottom of the graph. The temperature goes from a scale of minus 20 all the way, and they're looking at, in the next question, at 10 degrees centigrade. Well, if you look at 10 degrees centigrade on the scale, it comes out to 2 ohms. Okay, so that's the value we want to look at. And then deduce whether the circuit, this circuit would switch on the heater when the temperature falls below 10 degrees centigrade. So first let's look at 10 degrees. We said the resistance is 2, and then you can work out that the thermistor voltage would then be 2 here out of a total of 17. So it's basically this share, this will take 2/17 of the total voltage. Because remember, the ratio of the resistances is equal to the ratio of the voltages. So the voltage at T is equal to the EMF, which is this, multiplied by the resistance across here, divided by the total resistance, which is across the whole 6 volts. Okay? So once you do that, you do the ratio, and you will get the answer of 7.706, which is, remember, to switch on, you needed it to be approximately 0.70 volts, so that's more. So from the question information given, the heater switches on when the voltage at T is greater than 0.70. You need to say that. So at 10 degrees centigrade, we know it switches on, but the question doesn't ask at 10 degrees, it says what happens below, when it falls below. Well, if it falls below 10 degrees centigrade, when the temperature falls even lower, the resistance increases of the thermometer. Okay, this T is responsible for the thermistor. Did I say thermometer? I meant thermistor. The resistance of the thermistor will increase as the temperature goes below 10 degrees. Yeah, so if the resistance of the thermistor, so below 10 degrees, the resistance increases, so its voltage of the share of the voltage will increase more than 0.70, so the heater will be switched on at any value below 10 degrees centigrade, and that's the final mark. Each of these is one of the 6 points. Okay, so then says explain why the thermistor, and this is a common question it seems like, explain why the thermistor changes with temperature. Well, a thermistor is a semiconductor device, so an increase in temperature increases the number of free electrons or the number of electrons in the conduction band. Okay, so free electrons. So you've got the concept. So if that happens, yeah, remember I equals Na QV. So if that happens, more current means the resistance will decrease. Okay, hope that makes sense. Okay, the next question is question 15. Yeah, so question 15 is about a teacher demonstrating the behavior of electrons traveling through graphite. So the graphite and the electrons go through basically works as a diffraction grating. An electron beam was directed through a thin piece of graphite towards a fluorescent screen, yeah, also through a vacuum. You must realize they must go through a vacuum, otherwise the electrons will be absorbed by whatever is in there. You want it to be empty space. Okay, so that's what's going to happen, and you're going to get a diffraction pattern on there which looks like this. Okay, so it goes in diffracted in all directions, and you get rings forming with bright areas and dark areas and bright areas and so on. Okay, so that produces the diffraction pattern. The demonstration can be used to make conclusions about the behavior of electrons, yeah, and, which I circled it, the structure of the graphite. State these conclusions. So what can we conclude about the behavior of electrons, and what can we conclude about the structure of graphite? Well, for the electrons, first of all, the electrons must exhibit wave-like behavior, yeah, because diffraction is a wave property. Okay, so wave property is diffraction. So if electrons can diffract, then that means that they can exhibit wave-like behavior. They diffract as they pass through the graphite, yeah, obviously. That's what's causing it. So the electrons diffract as they go through the gaps in the graphite. And what does that tell us about structure? For the diffraction to occur, yeah, it must act as diffraction grating, yeah. So its structure must be ordered or regular, so regular spaces in between them, which is what a diffraction grating is. Okay, so it must have an ordered, rigid structure, crystalline structure, you could say. So there must be gaps that allow that to happen. The gaps in its structure must also be of a similar size to the electron's de Broglie wavelength. Okay, so the wavelength is lambda equals h over p. The momentum of the electrons determines their effective wavelength. Okay, so that's the beginning of question 15, and we'll probably stop at the end of question 15, leave the last 3 questions to a second video. Okay, so part B, the electrons were accelerated through potential difference of 2,400 volts, yeah, before interacting with the graphite. Show that the work done on each electron is about this much. Well, the work done on electrons comes from, yeah, work done could be the energy that electrons gain. If you do work on the electrons electrically, yeah, you're basically giving the charge a certain voltage to accelerate towards. So if you want to gain an electron, the electrons to gain kinetic energy, the energy will come out as kinetic, and you do that by putting a positive potential in front of it, which we've put 2,400 volts. So they will gain what we call 2,400 electron volts. Yeah, so this will create an energy of 2,400 electron volts, which you may be getting used to. So 2,400 electron volts would basically be the 2,400 volts multiplied by the charge of one electron to get it into joules. Okay, charge, so Q would be the charge of the electron, and V would be the voltage we've used, which is 2,400, and that gives you a value of 3.84 times 10 to the minus 16, which is approximately 4 times 10 to the minus 16 to one significant figure. Okay? So calculate the maximum velocity of the electrons. So remember that by doing this work on them, they will gain kinetic energy. They've accelerated. So the maximum kinetic energy gained by them will be whatever this value is. So you put the V max, so you want maximum velocity, will be V max. I suppose some of them won't get the same velocity as others. Yeah. So the maximum will be if they get all of this. So you put the energy on the right hand side, and then you change the subject, get V squared, you square root it. Yeah, so you take that off, put the square root over there, put it in your calculator, and it gives a number approximately to two significant figures, yeah, of 2.9 times 10 to the 7 meters per second. Okay. The final part is part 3. The accelerating PD was then increased. Well, if you're going to increase them, what's going to happen? Well, obviously they'll come with greater increased voltage. Voltage going up means kinetic energy going up. Kinetic energy going up means momentum going up. Okay? And momentum going up means lambda going down. Okay? The wavelength going down. So explain how the pattern, so once we know that, this is basically, you can work it out just by what I've just explained. Explain how the pattern on the screen would change. Well, the pattern on the screen looked like this, concentric rings. Okay, so what's going to happen to the pattern? If the PD increases, the maximum velocity increases, and momentum increases. So you get 1 mark for getting up to there. Since lambda is 1 over, or inversely proportional to the momentum, yeah, where P is momentum, that means inversely proportional, means the lambda of the electrons, the de Broglie wavelength, will decrease. Second mark. And since n lambda, since n lambda equals d sine theta, n and d don't change because they're the different numbers that we're going to look at, the first order, the second order, and so on. So this is the pattern. So the numbers themselves, for example, if n equals 1, you're looking at the first bright fringe, for example. D is a property of the diffraction grating. In this case, it's the graphite, the gaps between the graphite layers. Okay, so n lambda equals d sine theta. So as lambda decreases, yeah, so if lambda decreases, so must sine theta, because this doesn't change and this doesn't change. So the only thing that can change is sine theta will go down. So and sine theta, obviously, if sine theta goes down, theta decreases. Okay, because remember the maximum value of sine theta is when it's 90. So if lambda goes down, then we have to go below 90. So it's going to get smaller than 90. So the rings on the pattern would be closer. Okay, so the angles will decrease, so the rings would get closer. Because remember, the angle is basically how far apart they will spread, and that is why they decrease. I hope that makes sense to you. So that's the end of our first part of the run-through of this paper. And I've got questions 16, 17, and 18 to do. Once again, we are now over 175, I think, subscribers, so it's increasing each week. I think a lot of people are preparing for their exams. So good luck in your exams. If you're doing Unit 1 this week, you'll need to concentrate on that. So Unit 2 will be next week, so I'll try and get the second part of the video done as quickly as possible. So if you found it helpful, please give us a like. A lot of people are watching the videos, they put positive comments every now and then, but we're not getting anyone interacting through the thumbs up sign. We do want you to give us the thumbs up, please, so we get more people following us. And share it with any friends who are doing the same exam as you, because I think they'll find it helpful. And subscribe so you'll know when the next video will be ready. Okay, bye for now. See you in the next video.